Today we're talking about implementing remote procedure calls, the original paper responsible for the paradigm shift to abstracting many of the most complicated pieces of distributed computing. This paper originates from Palo Alto, California, the home of Silicon Valley, responsible for the lion's share of computing innovations over the past 40 years. And for context, in 1983, the year this paper was written, Microsoft's MS-DOS was just 2 years old. Apple Inc. had been listed on the stock market for only 3 years, and it had just released the Lisa, the first mass-marketed GUI desktop. We've already spoken about RPCs in class, but this paper marks a watershed moment in distributed computing. It was written by two computer scientists from Xerox PARC. If you don't recognize the name, you should. Xerox PARC Palo Alto Research Center is home to a plethora of innovations like the first laser printer, bitmap graphics, the graphical user interface, Smalltalk, which is the first fully formed OO language, Ethernet, and the computer mouse, among other things. Andrew Birrell and Bruce J. Nelson implemented a theoretical concept called the remote procedure call. There are several topics discussed in this paper, starting with the high-level overview of what RPC is, followed by performance tuning and other considerations relevant to how RPC was implemented. We'll start by discussing in a high level how RPC works, and then touch on some of the performance considerations discussed in this paper. What is a remote procedure call? Well, to quote the paper, the idea of a remote procedure call is quite simple. It's based on the observation that procedure calls are well-known and well-understood mechanism for transfer of control and data with a program running on a single computer. Therefore, it's proposed this same method be extended to communication across the network. Great, that's what it is. So why are we doing it? Turns out the answer is pretty simple. Abstraction and ease of use. Once again, to quote the paper, the primary purpose of our RPC project was to make distributed computing easy. So up until this point, only a small number of practitioners exist in distributed computing due to the complexity, things like shared address space and message passing. Birrell and Nelson wanted to change that and make distributed computing simple, removing the barriers to entry. Every programmer knows local procedure calls, so they built an interface that closely resembles local procedure calls. Prior to this point, RPCs have been mentioned in published literature since 1976, and Nelson was actually somewhat of an expert on the topic. His dissertation centered on remote procedure calls. While the general concept exists, Birrell and Nelson have just created the most complete implementation of an RPC up until this point. So how does RPC work? And more specifically, how does RPC work as described in this paper? Just as some context, Birrell and Nelson have implemented this in Cedars, which is a superset of Mesa. This is a new language that was created by Xerox PARC with several features, including garbage collection and memory leak checking. So if you actually go through and read the paper, they have a lot of contextual commentary on Mesa and on Cedars. But the stubbing process is owned by a software package they created known as Lupine, and that was written in Cedars. A remote procedure call starts with at least two entities, a caller and a callee described in the paper, or a client and a server, the nomenclature we'll be using during this video. So the client needs some kind of process completed. And in this scenario, let's just assume that it's not ideal or plausible for this process to be completed locally. Interesting side note, Birrell and Nelson knew the importance of this before they knew all of the applications. They make it clear in the paper that currently there were no practical uses for this technology. Networking limitations capped the speed at 10 megabits per second on even the most advanced transmission networks in the world, but they were able to see the potential and future for how this would change computing. So the user makes a procedure call which looks almost identical to a local procedure call. This is where Lupine comes in. Lupine is a user stubbing software package that takes the procedure call, packs it, and prepares it for handoff to the next stage, the RPC runtime. At this point, the RPC runtime on the user side transmits the package across the network to the server and transitions into a waiting state. We'll come back to this later because there are some interesting considerations Birrell and Nelson took into account for handling waiting time. So the server operates as almost a complete inverse of the user. The first line of contact for the server is the RPC runtime, which passes the received packet off to the server stub, also Lupine handled, which unpacks the argument and passes it as a local procedure call to the server. The server completes its portion and now repeats almost the exact same steps started by the user. It sends to the stub, which packs the argument, then hands off to the RPC, which in turn transmits the information back to the user. At this point, if you remember back on the user side, the RPC runtime has been in a waiting state and listening for the returning package. The user RPC runtime accepts the package, sends to the stub for unpacking via loopine, which in turn hands the result back to the procedure. The procedure sees this as an almost identical result to a local return. So that's it. That's RPC in a nutshell, and the implications of this are huge. Does this seem somewhat familiar? RPCs are actually one of the earliest examples of API interaction. In essence, the web APIs that have revolutionized cloud computing and automation are influenced by this groundbreaking paper. So despite being more than 35 years old, this paper is still very relevant. That's one portion of the paper, so let's talk about some of the performance considerations discussed. How did their RPC implementation handle transmission of data from client to server? It's actually quite interesting. They created a shortcut to reduce network congestion when calls were simple. And then they created a more complex way of handling data transmission for long-running calls. So starting first with simple calls. First, the client decides to initiate a call. When making the call, the client sends relevant metadata and procedure arguments and immediately logs a retransmission interval. So this is where they're saving some of the network traffic. When the client sends the file, they won't actually send any additional information until the retransmission interval has expired, at which point they'll resend the package. Now, the idea is they will receive a response before the retransmission protocol expires. Thereby, the response ends up being the acknowledgement from the server to the user. It's only if that retransmission interval expires that the client would send another message. When a more complicated call is made, the call includes a please ACK argument, requiring the server to acknowledge the packet was accepted. Most everything works the same, except that the client will continue to send periodic probe messages waiting for a response from the server. As the acknowledgement responses are received, the frequency of the probe message decreases until it gets to about 5 minutes between each message. If this seems familiar to you, it's because it most closely resembles the idea of exponential backoff, used frequently in software designed to reduce network congestion. And one of the last things worth mentioning is how the RPC paper proposed handling timeouts. So it's actually a little bit different than you might expect. There were no actual timeouts. In theory, the user could be stuck waiting for a server that is caught in a programming loop. In this way, Birrell and Nelson stated that it essentially was going to reflect the same problems that you would run into with a local procedure call, and left it up to the server programmer and user programmer to figure out how to deal with those types of timeouts. And that's it. That's the end of my overview on the paper. Please feel free to pick the paper up and read it. There is still a decent amount I wasn't able to cover in the short 8 minutes that we have. Thank you for listening.